So what did we talk about last time? Last time we kind of did this like calculus of variations stuff, which is kind of this like idea of how you minimize some function with respect to a function, aka sort of like optimize. It's really trajectory optimization is kind of like I would say the most sensible name for this, right? The idea is you're minimizing some function, some scalar objective function with respect to a trajectory or a function of time. The idea is it's a continuous function rather than just a vector. And so there's some tricks involved in this. And we did this a couple of ways, right? We discretized everything and did it kind of standard, set the gradient equal to 0 KKT condition style. Then we did it more the classic way where you do it using some like calculus tricks, right? This sort of integration by parts trick, and you can kind of do it in continuous time. And the result in both cases is a set of like local conditions that are really either ODEs or difference equations. They're local equations, local necessary condition equations. And this ends up being the Euler-Lagrange equation in the continuous time case, where it's sort of discrete finite diff analog in the discrete time case. And then we talked a little bit about, we kind of set up this hanging cable problem. Okay, so any questions about any of that stuff? No, all right. So today what we're going to do is kind of like fill in a few little gaps on that calculus of variations thing. And sort of look at it a different way that may be sort of more familiar if you have more of like a CSRL controls background. And then we're going to talk about, then we're going to start getting into like Lagrangian mechanics, kind of the classic stuff and motivating that and stuff. So we're going to talk about kind of how you can think about the relationship between like dynamics, equations of motion, and energy, which is kind of what this is all about. And then we're going to talk about kind of the Lagrangian stuff. And we're kind of like then kind of loop everything back and end up with the least action principle. Which is where kind of where all this stuff comes from. Okay, questions about anything? Okay, cool. So so let's kind of like go back in time in our brains to this hanging cable thing. Okay, so the setup we had like two supports like this that are kind of at known points, and we have this cable hanging down. Let's see, fixed endpoints. And what we did kind of first last time was discretize this, right, into a whole bunch of little discrete chunks. And what I want to do now, this time, is we're going to like zoom in on one little piece of this cable. And look at sort of this whole thing from another perspective. So here's this zoomed in like little segment of cable where we're going to just look at 3 nodes or knot points, whatever you want to call these things. And again, we're kind of zooming in and assuming that like if we zoom in close enough, the cable is locally a straight line between these little points. Sort of actually what I would argue that's actually the fundamental idea behind calculus. You zoom on anything close enough, it becomes a straight line. That's actually what it is all about. Okay, so this is, and we're going to give these kind of generic indices. So this is xk minus 1, xk, xk plus 1. The idea here is this is a generic little chunk of a couple of segments. It's 2 segments or 3 knot points, right? And we're going to zoom in super close, and this could be anywhere in the cable, right? I just picked a random spot, hence the generic indices, right? Weird. I didn't know that this did that. tried to straighten out my lines for me, which is kind of cool. But okay, cool. So let me write this down in words. So here's what I'm gonna say this, and then maybe we can talk about it. And maybe you guys have heard similar statements before. So the idea is, let's say we, this is a solution, right? We're looking at this thing. It's a real cable, whatever. It's hanging down in its like minimum energy state. We're just kind of zooming in and looking at this, right? So if we zoom in on this little chunk, this like small subsection, and if I like took a solution, right? If I took a solution to this thing, zoom in really close, and I take this little piece, if I were to take this little chunk out of the full cable, take this known solution and fix these points at the known solution as fixed endpoints, and then minimize this little piece with just respect to the middle point, that would also have to be optimal, right? Otherwise, if it weren't, I would have gotten a different answer for the whole cable, right? Does that make sense? So each little subsection, if I took a chunk out and I made a little cable with the same points, endpoints, taken from the big solution, and just minimize the little chunk, it would have to also be optimal. The little sub chunk would have to be optimal if it were taken out of, this optimal solution for the whole big cable. Has anyone heard things like this before? Can anyone tell me like a name for that thing I just said? Bellman principle, principle of optimality, blah, blah, blah. So what are we doing? That's the Bellman principle. What do you do with Bellman's principle? Yeah, everyone says so. Dynamic programming, right? So the idea is really with dynamic programming is that solutions to problems like this, like trajectory optimization problems of this flavor where you have like, say, fixed endpoints and you're minimizing some function of time, whatever, some trajectory looking thing, they have this property of like self-similarity as you zoom in. So if you take the whole thing, if I were to zoom in and take some little piece out and fix the endpoints on the little piece and minimize just the little piece, that solution to the little piece would have to be the same as it was as a like sub chunk of the whole big optimal solution. That's really what Bellman's principle is all about. Principle of optimality. It's saying that like for problems of this flavor, sort of trajectory optimization flavored problems, you have this like self-similarity at different time scales where if you zoom in, the little pieces have to be off. And this is common sense, right? It makes the most sense in the context of like shortest path problems, right? Where it's like, if there were a shorter way for this little chunk, you would have taken it on the big chunk, right? So here it's, minimizing potential energy for the whole chain. But the idea is if there was a way to make this little chunk with these fixed ends have lower energy, I would have done it on the big zoomed out full problem. Does that make sense to everybody? It's like a really common sense idea, but I feel like, surprisingly subtle, the implications of this. Okay. So small subsection also has to be optimal. And in this case, has to have minimum potential energy, right? That's what we're minimizing. I mean, seems like common sense, but this wasn't figured out until like the 1950s. I guess no one cared before that. But even in this context, this is way older stuff, right? This goes back to like 1700s, this stuff. But like the Bellman stuff was, 50s, 60s. Okay, so let's see, then saying a few more things like this. We can take any subsection and fix its endpoints. To the true solution. And this will look exactly like the original problem. Just smaller, right? It's the same cost function, same fact that it has fixed endpoints, blah, blah, blah. So it's like this self-similarity as you zoom in and go to smaller and smaller chunks, right? Okay, that cleared everybody? So we're going to take a vastly different approach to this whole least action thing. What we're going to do is use this Bellman principle idea, zoom in on the smallest chunk of cable that makes any sense, which is 3 knot points, right? Because I have to have fixed endpoints. So if I only have 2 points, there's nothing to minimize. So if I go to 3 points, I have fixed endpoints and I have 1 midpoint that I can actually minimize, right? So that's the smallest chunk that actually makes any sense in this context. So that's what we're going to look at. Three points. So just to make things easy, right, we'll call this, so this is fixed. And we've got x1, x2, which is the only free one, and x3. And then we've got the sort of, I'll just recall the stuff from last time. So we've got sk squared equals delta x k squared plus delta y k squared. This is the length constraint. And this is, if we kind of like remember from last time, I can play this kind of little, oh, I'm gonna just plug some stuff in here. This is a constant, so it's no indices, and then this is yk plus 1 minus yk squared. And then we can sort of pull that out and get this sort of sneaky little result from last time, where this is like the delta y stuff in here. It's a little bigger. We're gonna like pull the delta x out, right? From last time. So this is the delta y over delta x all squared. This is dividing through by delta x inside the square root. And that's the length. And then we have this potential energy deal. So individual little chunks potential energy is just 1/2. It's the y, it's y mg times height, right? Is the potential energy for this. So I'm going to do a midpoint approximation like last time. So I'm going to take the average height. So that's yk plus 1 plus yk over 2. And then times the density, times g, and then times the length of that segment, right? And if I plug everything in and sort of simplify this down using the trick from above, I get this. Again, we did this last time. I'm just kind of rehashing it so we can use it today and not forget stuff and whatever. Okay, k plus 1 minus yk over the delta x, oops, squared in here. And then this whole thing times the delta x. So that's just a little like basically midpoint sort of rectangle rule approximation of that little integral over that little guy. And then for this little chunk of cable, where that's all I care about, then the total energy is the sum over the little chunks. And I only have 2 chunks here, right? 1 chunk, 2 chunk. So the whole thing is just 2 pieces. So it's like this U1 of Y1, Y2, and then say U2 of Y2, Y3, right? So it's where these little U's are these guys, right? So this is just this chunk evaluated at so you need both knot points to evaluate this guy, right? It's a midpoint approximation. So I'm just going to kind of stick with this notation, nice and simple. So this big U is now, function of just the 3 knot points, Y1, Y2, and Y3. Cool, that's all there is. And the endpoints are fixed. So I literally just have to minimize respect to the middle Y2 when I do this. And remember, we also have the length constraint from so let's write that down. Okay, so this is the total length is the sum over all these little SKs for each little chunk. And in this case, that's just the two pieces. So S1, Y1, Y2 plus S2, Y2, Y3 has to equal the actual total length, which here is, we're going to call L1 to 3. So we use this L to mean the actual length of the cable. And again, if you were zooming in on a known solution, right, the idea is you would know what this was, or you have, just actually some length of cable hanging between two endpoints. This is a known length. And all I'm saying is if I add up all the little lengths for each chunk, it's got to add up to the known actual length, right? Cool. I guess we don't need indices on these guys. So they're just, that's a function. And if I plug in, yep. Yes, there should be one here, right? Is that what you were looking for? Yeah, cool. I think you're right. And also, yeah, these don't really need to be indexed because it's just the function is what it is. And I'm just evaluating it at these arguments. So we'll go with that. Okay, cool. Does that make sense to everybody? So that's what everything is. Here's kind of the stuff. And now all I've got to do for this little chunk is minimize with respect to Y2. That's the only variable there is to minimize with respect to, because everything else is fixed. Midpoint. So we get KKT conditions. So I'm going to take, partial respect to Y2 of this U of Y1, Y2, Y3, which is just this guy up here, right, that I wrote down. That's the sum of all little u's, which is only two pieces. And then I'm going to get my Lagrange multiplier term times this total length S guy. Again, it's just that stuff. So I'm going to write that as S, Y1, Y2, Y3. This thing has to equal 0 at an optimum. And I can kind of expand this out a little bit. I guess maybe this was overboard, but and remember here, there's only a single lambda because it's one constraint, right? It's not a per time step thing. It's just for the whole cable. Okay, so there's that. And now I'm going to actually go take these derivatives, and I'm going to use that slot derivative notation from last time. So we, like it's just derivative with respect to whatever argument. So here it's D2 of this guy and D1 of this guy, right? So we get D2 U at, so we got this thing, we got our sort of necessary conditions. This looks very much like what we had yesterday, right? This is Y2, Y3. This whole mess has to equal 0. That's what we're doing. Okay, so from last time, and like our discussions about, this kind of thing, this thing is called the discrete Euler-Lagrange equation. And it looks, this is exactly the same kind of thing we derived last time, right? And last time we did it by looking at the whole sum over the whole trajectory, minimizing with respect to all the knot points, and then playing some games with index manipulation to line up the indices inside the sum and pull some stuff out. And then we got to this guy, right? We also did this last time in continuous time and used like the whole trajectory and took this variational derivative thing and played some like weirdo integration by parts tricks to get the continuous version of this, right? Here we got this a completely different way. We got this by drawing a little cartoon picture, making some hand-wavy arguments about optimality and Bellman's principle, zooming in this little chunk. And now I only have to minimize with respect to that little midpoint chunk, and I got the same answer, right? That's cool. So let's maybe write something about that. This matches what we got last time. by minimizing the whole sum. And this time we only, let's see, what was I going to say about this? I can keep talking while this figures itself out, maybe. So we talked about this looks, like dynamic programming. That's what it is. It's not super surprising. Try this again. What else did I have to say about this while this thing thinks? Oh yeah. So the gist of this is we did this little chunk. We got this nice little difference equation. Y1, Y2, Y3, whatever. We get these optimality conditions. Those conditions really are like, but remember at the beginning we said, this works for any little chunk, right? Those indices can be generic, so I can actually slide that anywhere I want. And it's an equality constraint. It's like an algebraic condition between like any three neighboring knot points, right? So given any two of them, I can solve for the third one. So in particular, if I'm at one end, if I know Y1 and Y2, I can solve for Y3. If I know Y2 and Y3, I can solve for Y1, right? I can run that thing forward or backward. And so if I can bootstrap it on some initial conditions at the beginning, I can use that to solve for the entire thing. And I'm only solving these little tiny chunks one at a time. I don't have to actually solve the whole big optimization problem. So this is kind of how we can get away with this because of this like self-similarity property, right? Of the thing looking the same if I zoom in onto smaller chunks, which is pretty cool. Okay. But I can use this discrete Euler-Lagrange equation for any of Y1, Y2, Y3, given the other two. Okay, so as just a quick aside, I'm not going to do this. I did this last year and I didn't think it was that useful. Sort of unsurprisingly, I can take that equation right there, and I can take a limit as delta x goes to 0. What do you think is going to happen if I do that? I'm going to get the continuous classic Euler-Lagrange equation. I'm going to leave this as bonus points for anyone who wants to do it. It's not actually that hard. It's like 10 lines of math. So if you want bonus points. Oh, yeah. Okay. Looks like some people got figured out there somehow. Okay. So we take the continuum limit as delta x goes to 0. You're gonna get basically this guy. What should I call this now? We'll like call this L to be sort of, which is the, we'll allude to things to come, where L is the little u guy. Plus the little length constraint guy, the Lagrangian, right? Lagrangian in the optimization sense, which is almost the same as the mechanics Lagrangian, but irritatingly not exactly. And so we can easily get out the sort of continuous Euler-Lagrange equation. Okay, so this is kind of fun. We got the like classic Euler-Lagrange equation stuff without really doing any calculus of variations, right? So we instead can like invoke this like self-similarity Bellman principle idea, kind of do this in discrete land, and then just take a limit of the answer and get this guy. So take your pick, calculus of variations, Bellman principle, same stuff actually. The Bellman principle stuff is much more recent, right? That's like 20th century stuff, more computer science-y, control-y flavored. The calculus of variation stuff is like 300-400 years old, back to like 1700s. Personally, I think this makes a lot more sense and is like a lot more intuitive and gives you some insight, maybe, hopefully. So let's see, what can we say about this? Yeah, I will write this in words now. So the fact that every subsegment has to be optimal lets us derive local optimality conditions. So when I say local, I mean it's a condition on a little chunk, right? Or some differential piece or some little tiny chunk, right? That's what we did. And the idea there is that now you could bootstrap on that and solve the whole problem by only solving a bunch of little problems instead of having to solve this whole giant optimization problem in one shot, which is a lot harder to do, right? And that this thing is, these local optimality conditions are Euler-Lagrange equations. The other kind of point is this Euler-Lagrange equation, you probably heard it right in like a mechanics course, but it's actually generic to any problem of this flavor, this like trajectory optimization flavor. The first order necessary conditions in continuous time or whatever, continuous necessary conditions for any problem of that flavor is a Euler-Lagrange equation. So Euler-Lagrange is actually like the continuous analog of KKT is actually what this is. Those are just the continuous limit of these KKT conditions, right? Does that make sense? In discrete time, this discrete Euler-Lagrange equation, we got that from KKT conditions, right? If you do a limit, blah, 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 and it's continuous Euler-Lagrange equations. So those are kind of the same thing. Make sense? Okay, so this like kind of idea of like exploiting problem structure, i.e. this self-similarity thing, this is called the principle of optimality or Bellman's principle. And we already said this, I'm just writing it down for posterity. Or Bellman's principle after Richard Bellman, who basically is like the father of dynamic programming. And this idea basically underlies all of like optimal control, dynamic programming, reinforcement learning, et cetera, et cetera. So it's a deep idea. And I guess the main takeaway is these problems all are kind of the same flavor. They're all like sequential in nature. They have some time, right? And you're really optimizing like a sequence of, you can think about it as a sequential decision problem. That's sort of the dynamic programming flavor, or just really as a trajectory in time, right? Where you have sequential things happening in time and that like you have this self-similarity zoom in property. So the one little, so these are like some fun nuggets that hopefully are making some things click in your brain with things you've already seen before. I'll make this a little bit more explicit. So check this out. We can also view this whole thing, this like cable thing or the mechanics problem or whatever, which we're going to talk about in a sec, as an optimal control problem. Let's see what that looks like. So the problem we're sort of solving has this kind of flavor, min over y of x, this trajectory. We're minimizing the potential energy, which looks like this, from 0 to L, u of y comma y dot. This is the continuous time version, right? Dx. So this is the potential energy. And then we've got endpoint constraints, y naught, equals whatever is given, and then y L equals sort of this endpoint condition. I guess we'll call this y n or something. So we've got, and then we also have the length constraint, right? So this was like S equals some like set, length. Okay, so this is potential energy. And then these are these endpoint conditions. And like the length constraint, we won't really worry about that right now. It's a detail. You can do it. It's not a big deal. So this is the problem we just solved. I'm now going to write down a standard form optimal control problem. So this is like min over x and u. Oh, this is the wrong color. So we have some cost function. Who's done optimal control before? Done some control stuff. Okay, so hopefully this will make some sense to some of you. If you haven't seen this before, then I guess this is going to be lost on you, but I think it's cool. So we're gonna, oh, I guess this is an overloading of notation. That's kind of bad. Sorry. This is called your stage cost, right? And then I've got dynamics constraints. X dot equals f of x u. And I've got initial state constraint, say, and a goal constraint where I want to steer the system to at the final time. So let's like write those in. This is dt. So this is your cost. Dynamics. And then initial state, goal state. And we've got this sort of like one-to-one correspondence between these problems. Which is, so our potential energy is our cost function, sort of trivially. Our x variable, which is the, the x coordinate on our cable, is time in the optimal control setting. We've got y of x, sort of our height, right, as we go along, mapping to our state x of t for the control problem. And then what does the control input actually look like? What's the control up here? This is like maybe a little bit subtle. Yeah, that's so it turns out the mapping here is that like the velocities actually more or less end up being your control inputs. And you can make this more explicit by introducing a new variable and then adding a constraint for y dot. So basically what this looks like is the dynamics constraint looks like x dot equals u. So if I went up here and introduced a new variable in this problem, u, and wrote a constraint down here, y dot equals u, that y dot equals u would be like a trivial dynamics function, right? It's an integrator dynamics, and then it would actually be exactly in this form. So this would be, actually, let me write it the other way, like, so y dot equals so yeah, so this cable problem and also all of dynamics that we'll see in a sec is like a special case of an optimal control problem where you have this trivial dynamics, y dot equals u, where basically your controls end up being your velocities. You can actually set the problem up that way. Usually we don't, right? We usually write it this way, but you can easily do that and introduce like a dynamics constraint, and it's exactly an optimal control problem now. Okay, Hopefully that was like a fun little interlude. Any questions about anything here? This is super non-standard. This is very like Zach stuff that I don't know. Hope you enjoy. These are all my good little nuggets that I'm like just handing you. So I hope you appreciate this. This is not in any books or anything. Okay, cool. So with that, this ends our tour of like calculus of variations, dynamic programming. They're kind of the same thing, blah, blah, blah. Control is dynamics, is everything's a hanging chain. I think that sort of sums that all up. So we're going to sort of switch gears now, and we're going to say, okay, so far I was just teaching you math, right? I was just teaching you like this dynamic programming, calculus of variation stuff. And we did it in the context of the hanging chain, because I actually think the hanging chain captures all the key little nuggets. In particular, the thing that's super clear with the hanging chain that is not clear when you solve generic dynamics problems is where that endpoint constraint comes from. With the chain, it's super obvious. You got to have fixed ends to hang the chain from. When you go do it for physics, and you're doing like actual dynamics problems, you still assume fixed endpoints, but it's way less clear and intuitive like where that comes from. The answer is it actually just comes from the math. In order to make this self-similarity argument, like dynamic programming argument work out, you have to have fixed endpoints. And then like this idea of like I can zoom in and have fixed endpoints, it's necessary for that like dynamic programming thing to work out, is the fixed endpoints. But once you the local optimality conditions, you don't care anymore, right? So it's necessary to make the math work, basically, and it's super clear in the chain example that has to be true. It's not clear in general. So hopefully that made some sense in your brains. Okay, cool. Now we're going to talk about actually doing physics with this. So like this whole setup, how do we actually do mechanics from this? Where does this like whole Lagrangian and mechanics come from, blah, blah, blah. And the kind of, I'm going to try to like motivate this a little bit and show you some other little quirky things, and like where maybe these ideas originally came from, and how you could maybe think about sort of inventing this for yourself if you had to. So what we're going to kind of talk about is dynamics from energy. So, you know, and we're going to look at the most trivial mechanical system, you know, you could think about. So system. Yep. Okay, getting better at this. Okay, so here's what we got. Everybody's, you know, favorite linear system, spring and a mass, M and K. We've all seen this before, and we got some X coordinate. Cool. Okay, so we all know what this is, right? We got mx double dot equals minus kx, blah, blah, blah. So here's where it's going to get a little interesting. So let's think about this. This is a conservative system, right? As I've drawn it, there's no damping, blah, blah, blah. So let's write down the total energy. We've got kinetic 1/2 mx dot squared, and we got potential 1/2 kx squared, right? We all know this stuff. Kinetic energy cool. Okay, so if I have no damping, which that means the total energy's got to be conserved, right? Okay, so I'm going to call that t plus u, right? We got this thing, 1/2 mx dot squared plus 1/2 kx squared plus h, and this is a constant now, right? Okay, so if this thing is constant, that means its time derivative has to be 0. Trivial. Okay, so now I'm going to do that. So we'll take d dt of h, and I'm just going to chain rule this, right? So I got so the 1/2 mx dot squared is going to become mx dot times x double dot, if I chain rule through that guy. And then the kx squared, 1/2 kx squared is going to become kx times x dot. Okay, so this has to equal 0. Now I can, like just looking at this, I can go ahead and divide through everything by x dot. And then, hey, look at that. I magically got my dynamics equation. That's cool. Thoughts on this? Has anyone done this before or tried this or thought about trying this? Okay. This gets me my dynamics. And if like all I had to do is write down energy, conserved quantity, whatever, and you could think about generalizing this to the damped case or whatever by adding in a little term that's like accounting for the energy loss or something. So why don't we just do this? Why do we need all this like Lagrangian, Euler-Lagrange, Hamilton's principle stuff? What's wrong with this? Anyone have any thoughts on that? I'll give you a hint. Why didn't I do the pendulum? Turns out it doesn't work super well for the pendulum. Okay, so the key thing here is this works. This actually works like in a surprising number of settings, but it works for any system. If anyone has thoughts, you can still speak up. It works for any system that looks like this. So where Q is like my position coordinate or whatever, my generalized coordinate. So in particular, it works if the M there, the mass matrix, is constant. Which is sort of trivially true for this problem because M is a scalar. But in a lot of cases, if you're choosing, joint coordinates for your robot, for the Qs or whatever, that M is not constant. It's M of Q. So like, let's kind of work this out, right? So if I take that form of H and I do H dot equals, if I just chain rule through this guy using the standard recipes, I'm going to get, that's M Q double dot plus partial U partial Q dot equals 0. And I can pull out the Q dot, right? And I can write this whole thing as Q dot transpose M Q double dot plus grad U of Q. And then I can just pull out the Q dot, like divide through by Q dot, right? Kind of thing. Not really dividing, but same kind of argument. And I can get out sort of your standard looking dynamics equation where this is the gradient of our potential. So we know minus grad U is our force, right? So if I move this over here, this is minus grad U, that's F. This is MA, right? So that works. That's cool. But it unfortunately turns out this doesn't work if M of Q is not a constant. Or sorry, if M is a function of Q, right? So another way of saying that is this idea, as we wrote it here, is not coordinate invariant. If I use different coordinates, so this works in, basically this works in Cartesian coordinates, where like M is constant, aka a flat metric, it's your fancy like physics words. But if M is a function of Q is varying, which is the case in most ways we write this down for robots where we have joint coordinates or whatever, this breaks. And that's because M is non-constant. And like basically we're using some other coordinate system, joint coordinates or whatever. So this idea that this thing that I wrote is not coordinate invariant. The gradient of this scalar energy thing that I take here, this time derivative, whatever, is going to change in different coordinate systems and give you wrong answers in general. It sort of breaks this idea. So, this is very enticing though, right? It works sometimes. And like the idea that I can write down some scalar energy function, take a gradient, and like get the answer is pretty magical. And it's very tantalizing for people for a long time. So people like stared at this and came up with like, some tricks to figure out how to do this. So I'm going to kind of like present a very like backwards way of motivating this that I think is actually more like historically how it actually went down. And then, so a slightly different setup that actually works. And you have to, looks like my battery is gonna crap out pretty soon, so I have to move this back. So what I'm gonna do now is, like we all kind of know where this is going. I'm gonna define some L that's T minus U instead of T plus U. And knowing what I want the answer to be, I want it to look like MQ double dot plus grad U equals 0. This is what I want the answer to be. If I kind of stare at this for a little while and think about it a little bit, it turns out I can sort of like backwards pull out this thing. So if I think about this a little bit, this guy, right, if I did so if I take it, that's a way to get MA. And then, this term is going to give me the minus grad U force term. And this thing equals 0. Cool. So that works out like sort of trivially just by like this kind of dumb hand wavy argument. And like, people looked at this and figured this out and sort of made this little thing up. I'm going to move this back so I can reach the outlet and not have my battery die. Okay, so the real magic here is this version. And this is not like some magical thing that like you have to kind of show this in a post hoc way if you're going at it this way. It turns out this one is coordinate invariant while the other one is not. And there are kind of deeper reasons why, but trivially we can see that. I'm going to just show you that it is real quick. So what we're going to do is plug in an arbitrary coordinate transformation and then chug through that equation and see what happens. We're going to plug in, so Q prime equals some F of Q, right? So this is the new coordinates. And then if I just sort of chain rule this, I get Q dot prime equals df dq times Q dot. And we're going to call that df dq thing J of Q, J for Jacobian. Okay, so what we're going to show now is we're going to plug in L of, so we're going to write L of Q prime, Q dot prime in this new coordinate system. And this is going to be L of F of Q, J of Q, Q dot, right? If I plug the coordinate transformation right in here, right? And so the idea is what we want to happen is I want to plug this sort of prime coordinate version into the Euler-Lagrange equation and show that at the end of the day, I get the same exact dynamics. So let's go ahead and do that. So I'm going to plug that guy with the coordinate transformation into the Euler-Lagrange equation thing. So this is going to be d dt of, so now it's going to be partial L partial Q dot times J of Q. And then I'm going to get partial L partial Q times J of Q. And then I'm going to get partial L partial Q dot times ddq J of Q, Q dot. That's just me like expanding out, right? And we want this whole thing to equal 0, blah, blah, blah. So if I kind of stare at this a little bit, I can pull out the J's. That's what I'm going to try to do at least. So I've got now d dt partial L. I'm just going to group terms sort of. J of Q plus dl dq dot partial J. We're going to be a little sort of loose here. I'm just like sort of rearranging stuff and expanding terms out. Okay, this whole thing. So now these two guys cancel out. This whole thing has to equal 0 again. Okay, so now, after all that nonsense, I get something that looks like this. I get my Euler-Lagrange equation, but in the prime coordinates or whatever. Or sorry, this is with the coordinate transformation smushed in there, right? So it turns out what ends up happening is I get my original Euler-Lagrange equation multiplied by this Jacobian, which sort of makes sense, right? Like I went and diffed a whole bunch of stuff. I get this Jacobian kind of, and it turns out that there's this magic cancellation that happens in here such that all the weirdo coordinate dependent terms basically cancel out. And then it works out such that I have original Euler-Lagrange equation times this coordinate change Jacobian thing. And I can now argue that, you know, this has to be true no matter what this is. So I can just get rid of that guy, right? So I'm back to my original Euler-Lagrange equation. Cool. So sort of the takeaway here is that the thing that makes this all work is that these two terms cancel out when you do it this way. And these terms actually have all the parts that like are actually dependent on the coordinates. Whereas the other version like basically doesn't have this magic cancellation. And like that's kind of the secret. And so the message here, overall message is the Euler-Lagrange equation looks the same, is exactly the same in both the Q and Q prime coordinates. And remember, I plugged in some arbitrary F coordinate transformation. It can be nonlinear or whatever, right? Okay, so that's sort of, I just proved to you that this thing is coordinate invariant. If I do it this way, I can use whatever arbitrary like joint coordinates, blah, 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 always works. This is sort of a different argument. The other kind of sort of maybe deeper story here is that we also know that this thing from our, you know, last 2 days, we also know that this thing is the first order necessary conditions, KKT conditions, right? Of an optimization problem. And that problem is the following, right? So min over Q of T, we're going to call this S, T naught to T final, L of Q and Q dot in here, T. Right, so this is what we did last time. And it so happens the first order necessary conditions for this are this Euler-Lagrange equation thing that we already have looked at a bunch for the hanging chain. And it just so happens, right, in this particular case, if I plug in this L into this optimization problem, I get this guy, right? So the reason we kind of went through this whole thing is sort of twofold. Okay, so this S is called action in like classical physics. This L is called the Lagrangian. And this is where the annoying like overloaded naming in different fields sort of comes up. This L is kinetic minus potential energy. This is called the Lagrangian in physics. In optimization, the Lagrangian is the objective plus Lagrange multiplier times constraint thing. They do coincide in physics when you have constraints. So if I have constraints in here, then it's this guy plus the constraint term. That whole thing is the Lagrangian. You still call it the Lagrangian in physics, but we also still call it the Lagrangian in physics when it's just the like stage cost, like objective function, which is sort of annoying. Okay, so, and then this optimization, really this optimization formulation is like deeper in some sense. And historically it did go the way I just showed you, where it was like, hey, look, if we do this, it's magically like a coordinate invariant version of F equals ma. That's how it actually went down. And it wasn't until like decades later that people figured out that this was actually like KKT conditions for this optimization problem. But that provides some sort of more key insight, right? So kind of, if it is like a minimum of this optimization problem, it can't matter what coordinates we use then, right? Like if I plug in some coordinate transformation, if it's the bottom of the bowl, it doesn't matter how I write the bowl down, right? Like what coordinates I use to represent the bowl, it's still got to be the bottom of the bowl, right? So this thing like kind of has to be coordinate invariant by virtue of being this like optimization problem with a minimum. The other way, it's sort of a, hey, look, this is a neat trick that just kind of falls out, right? But this way, it's clear that it has to be coordinate invariant. Okay, so vocabulary. That's called action. That's just an old physics word for this thing. And so this problem where I'm minimizing the action with respect to the trajectory Q of t is called the least action principle. Also called Hamilton's principle because Hamilton sort of discovered / invented it or whatever. But I always like descriptive names more than random dudes' names. So I will call this the least action principle because it actually means something to me. Incidentally, Hamilton also invented quaternions. Sure, also things we talk about in here. Okay, let's see. And so here's some more like things about this, right? So I would argue that this is really the most general way of writing down and thinking about dynamics, and that you can derive basically every other sort of form of mechanics or whatever from this. This is sort of the most general sort of like way to go. It doesn't matter what coordinates you use, right? All this other stuff. And I can also set this up in various ways, right? I can introduce like new variables and new constraints and write it like as a control problem. I can do all kinds of weird things, right? And if you've heard of like all these other formulations of dynamics, like, you know, Hamiltonian mechanics, Lagrangian mechanics, Keynes equations, the Gibbs-Appel equation, there's lots of these things, right? Turns out those are all just derived from this. And it's basically like plugging in particular choices of variables and like constraints and stuff like this, and then minimizing this guy, and out pops a new formulation of mechanics, right? So they're all just this. So if you know how to do this, you kind of like, that's it. You know how to do everything. And you can invent your own new formulation of mechanics if you want to. Cool. And yeah, have anyone heard of these other ones? There's like a million of these like formulations of classical mechanics. They're all literally just like choices of how you set this minimization problem up and like what variables you use and what constraints you plug in. And then you write down KKT conditions, and the KKT conditions for that are, you know, formulations of mechanics or whatever. And then, yeah, kind of the major advantage here, as we kind of already said, is I can pick whatever coordinates I want. For Q. You can do other fancy things too, but yeah, like you have a lot of flexibility in how you set that up, and you don't have to care about coordinates or coordinate transformations, any of that crap. You just like write down the minimization problem, minimize, and you're good. Okay, so we'll do now like the example I said we didn't do before because it doesn't work out the other way. We'll do the trivial pendulum example. And then I actually forgot to show you the other example when we did the hanging chain. I did the hanging chain numerically. So we'll do that too in the Jupyter notebook after this on the way out. So everyone's seen this before. We're just going to kind of go through the motions here concretely. So we've got a theta, we've got an M, we've got an L, we've got kinetic energy. So 1/2 mv squared. In this case, if we're using theta, it works out to be 1/2 ml squared theta dot squared. If you do a little trig, kinetic or potential energy is mg y or height or whatever. And if I write this out and do a little trig, it's mgl 1 minus cos theta. So I'm not using Cartesian coordinates, right? I'm using like polar coordinates or whatever. I'm using this theta because I like it and that's easier to write down this way. And if we write down our Lagrangian and turn the crank, we don't have to care about the coordinates. That's sort of the main takeaway. So I just write that stuff down. These are all scalar things. You'll hear people say that, oh, it's because I'm like, it's a scalar quantity that has to be coordinate invariant. That's kind of not true, right? Like we did it the other way with the total energy and it doesn't work out. So it's not just that it's a scalar, it's actually there's some like magic secret sauce stuff in that specific setup where some things cancel out on you. Okay, cool. So there's my Lagrangian. I plug into my Euler-Lagrange equation. I get ml squared theta double dot plus mgl sine theta equals 0. And that's my equation of motion for my pendulum that we all know and love. Cool. You've probably seen this before. Hopefully now this is like where this stuff comes from is a little more clear. Okay, so let's do the fun stuff now that I forgot to do before. Apologies. Jupyter notebook. So this is the hanging cable done out like as an optimization problem like we talked about. And this is on your homework. This is homework 2. This is like the meaty homework second problem on homework 2 or whatever. Hopefully this doesn't give me lots of pain. It ran last night just fine. Okay, it looks like we're okay. So here's all the setup. So, G, whatever, the full width between the supports is 10 meters or whatever you like. Length of the cable is a little longer than the gap, right? So 15 meters. And then mass of the cable, whatever. Number of discrete segments, we're going to make it 25, just arbitrary. So this is delta x now is right the width of each segment in terms of x coordinates, and then this density is just m over l like so this is all the stuff we had in the problem setup, right, as we wrote it out. So here's this cable total cable length. I'm going to write it sort of. So it turns out the solver we're going to use, this is a nonlinear problem, and IPOpt, the solver we're using, turns out it barfs if you try to do this without introducing the y dot variable. It just doesn't like it. I don't know, it's non-convex, whatever. So I'm going to introduce the y dot and we'll add that trivial dynamics constraint. But here's that length, right? So I'm just adding on, this is the discretized thing. It's exactly what we wrote in the notes, right? So it's y dot in here instead of, yk plus 1 minus yk over delta x. I just introduced that variable. Cool. So that's how we can write our length constraint down. Here's the potential energy, just like we did, right? So this is that midpoint y that I'm computing. And then I'm just plugging it into, rho g y times the little delta s or whatever. Same stuff we did before. Okay, so now to make it like slightly interesting, I'm going to make the endpoints a little bit different. So one's like higher than the other. Cool. Here's my objective function. It's just the total potential energy. This is the thing I'm going to minimize. And then I have some constraints. So I have an initial state constraint. I have a terminal state constraint. I have the length constraint. And then I also have a dynamics constraint because I'm using these explicit y dot variables. So this is basically like, it's actually midpoint integration, it turns out. This is equivalent to implicit midpoint integration, which we all know is the correct low order integrator to use. Okay, cool. So that's everything. I'm going to set this. This is all boilerplate code for calling IPOpt that I'm going to give you in your homework, so you don't have to write this yourself. But it's really not very insightful and it's kind of annoying. I'm using forward diff to evaluate gradients and stuff. Cool. All the rest of this is literally just boilerplate garbage that we shouldn't care about. Okay, so I'm going to make initial guesses, just all zeros, sort of dumb. I'm going to call the solver. Bam, solves in like under a second. Cool. Turns out it does not work if you don't introduce the y dots, which is interesting. And then we can plot this. Cool. And yeah, so one end higher than the other, and it looks like, you know, what you'd expect a hanging cable to look like. Cool. So this is the like me solving the whole problem all together at once version, right? What you guys are going to do on the homework is you're going to do the discrete Euler-Lagrange stuff, the continuous Euler-Lagrange stuff, first order, like all these nice little local optimality ideas that we derive, and sort of compare to this and show that you get the same answer and how these things kind of match up. And when we want to try anything, we can like move these heights around, play some weird games. I don't know. Anyone have any ideas? What should I do? Oh, it'll definitely barf. You want to try it? You want to be sadistic? Okay, so let's see. So yeah, if it's set at like 10, which is definitely too short, or let's make it 9. I'm sure the solver will bark at me and say it's like infeasible, but let's give it a try. What does it do? Optimal solution found. Oh, wow. I did not expect that. What does this look like? Oh, something weird happened. It's very broken. Oh, I did segments instead of length. Sorry. What did I do? Okay, where did I? Oh, oh yeah, that's my bad. I made it just coarser. Okay, so I wanted to change length here to like 9. Cool. Let's see now. I feel like this is not an interesting thing. This is just trying to be mean to the solver. So yeah, it's clearly unhappy now. It's not converging. So it should kick out and barf at us and complain, but it might take a while. Okay. Anyone have any other fun ideas to try? There's definitely other fun things to do with this. Okay, cool. What does it say? Yeah, lots of iterations. It should end up with an infeasible subproblem in here, which it should eventually sort of just crap out at us. What does it say? It doesn't say anything interesting. I'm sure it's like reached its maximum iterations or something like this. Did it say actually? It should have like an exit code up here somewhere that says how it quit. I think it just sort of reached a max iteration count and left. So IPOpt, because these are non-convex problems and life is hard, it actually tries to like, I think it just hit a max iteration count. Yeah, and does something that like seems vague, but it can't satisfy the constraints, obviously, right? Because this is non-convex though, like there's sort of no way of actually knowing. And so what this thing is doing under the hood, which we could talk about, I don't know, this is interesting to you. IPOpt, what it'll do on a problem like this is try to relax the constraints into penalties, like soften them, and then churn and churn and churn and see if it can do any better. And I think it was doing that and just hit the max iterations that we allowed, and then return this straight line thing that obviously doesn't obey the length constraint. So that wasn't super interesting. I don't know. Anyone have any other fun ideas? No? Oh, nothing? Yeah, okay. We can play around, try some other things, but you get the idea. Yeah. Yeah, that's a good question. Yeah, it's probably not going to have a unique answer. Actually, a better question is like, what happens if it's like some other number? You know, I don't think it actually matters a whole lot. Let's try like a really small number for gravity and see if it changes the answer. Yeah, I think it doesn't actually matter a whole lot what the actual gravity is. The interesting question though is, what if can I flip the sign on this? I think it'll probably barf at us, like, because there won't be a minimum, right? It'll be like sort of the cost function will be 0. So any solution will any solution will be trivially optimal. So it'll probably just spit back the initial guess or something. So yeah, this makes no sense and is just garbage noise probably, because the objective is it's trivially optimal, right? anything that obeys the length constraint is optimal. We could try, I kind of want to try flipping gravity and see what happens. What it should do is go the other way intuitively, right? It should go up. See if that actually works out. Yeah, hey, look at that. It does what we expected. That's cool. Yeah, I don't know. Some things you can do with this. Turns out the upside down solution is called a catenary. Has anyone heard that word before? I think it's on the homework. So this is the optimal shape for an arch under its own weight under gravity, which is kind of cool. So you'll actually see this shape is in a lot of building arches. This is like the correct shape to make an arch. Although it changes if it's loaded. So like it's the correct shape for a free arch that's only supporting its own weight. So the gateway arch in St. Louis is this shape, which is kind of fun. You will see them in architecture a lot. It sort of looks like a slightly like stretched up parabola. If I make the endpoints equal. Anyway, that's kind of fun. Anybody else? Any ideas? So I'll post this code. This is like helper starter code for homework problem 2. The rest of that is like the stuff we just did, today and last time. I think that's all I got.